Hello, everyone. So to kind of set expectations, we have 2 sessions on DocumentDB for Ignite. Today, I'm going to tell you a little bit about why do I personally just love this thing? Why do I love Azure DocumentDB? What does it solve in terms of the problems? Hence, I'll talk about the 3 V's of big data. I'll kind of give you an overview and evolution of what the NoSQL landscape looks like and where it's headed. And I'll also talk a little bit about, what the heck is this thing? What is Azure DocumentDB? And when is it a good fit? So I'll kind of tell you a little bit about how people are using it today. In tomorrow's session, assuming you guys are all really excited and think this is as cool as I think it is, I'll tell you everything you need to know to be successful when you're building an application on DocumentDB. That includes best practices like data modeling, how do you partition your data, how do you scale this out, how do you replicate across geographic regions, and also tell you a little bit about our roadmap on where, at least from my perspective, where our product is headed next. So what the heck is the 3 V's of big data? Why do people keep talking about it? I think, okay, my personal opinions are this is a little bit of a buzzword, but there's actually some element of truth behind it. So the 3 problems of big data that a lot of people like to talk about are volume, velocity, and variety. The problem of volume is I have so much data that it no longer fits on a single box. Or I have so much requests per second that, once again, one box cannot handle this. My CPU is running hot. I'm out of memory. I'm thrashing. I just don't have enough disk I/O. So what do you do to solve this problem? And in general, the concept here is you're going to scale out rather than scale up. Scaling up is always the concept of, I'll just buy some more memory, buy some more CPU, and life will be good. But the thing is that once you hit a ceiling, which is whatever the latest hardware is, the fact is there is a ceiling for scaling up. And so the only way you can actually scale, in theory, to infinity is to scale out. You basically buy more and more boxes, and you partition your data across that, your requests across that, because you can always add more boxes. The problem of velocity is how do I write responsive applications? And so it's good and all that you can get high throughput and you can store a lot of data, but how about in terms of latency? How do I actually make sure that I can build really, really snappy applications, right? You ever play a video game with really high latency or go to a website that takes forever to load? It sucks, right? So how do we solve that? And then the problem of variety is it turns out not all data is got a very rigid structure. Examples of this are, if you have, let's say, an IoT scenario, you have lots of different sensors, lots of different hardware. Each generation of hardware might have different sensors. How do you actually cope with if each of these things emits a record that looks a little bit slightly different? And I'll kind of talk to you about how do you handle data that tends to evolve, that tends to change shape, and this also might happen when you're iterating on an application very quickly. If you want to quickly get, let's say, beat your competitors to market, how do you actually just speed this up and reduce this friction? So at a heart, this is what NoSQL databases solve. And NoSQL actually has a pretty long history. It dates back to the 50s and 60s, but they weren't really mainstream until the late 2000s. And so what happened in the late 2000s is we saw our first wave of tech giants like Google, Facebook, Amazon, who found that, relational databases, they just can't keep up with the volume of data that they need. And so the very first problem they actually sought to solve was volume. And they sacrificed a lot of things. They got rid of things like transactions. They got rid of things like consistency, all in the name of just being able to scale and handle high volume of data. It turns out it really sucks developing on an application, a database that throws away things like transactions and consistency. And so what we saw was an evolution of NoSQL. In 2009, we saw our first wave of commercialized products for like MongoDB, React, Neo4j, solving different things. MongoDB is a pretty widely popular document store. Neo4j is a pretty popular graph store. And a lot of the things that they brought back was queryability. Basically, it turns out that when you really simplify data and scale out for the early databases, they just gave you key value access. And that's great when you want to query something by the primary key. It really sucks when you go, hey, there's this other field I want to query off of. How do I do that? In 2010, we started Project Florence here at Microsoft. This is what eventually becomes DocumentDB. What we wanted to do was build a cloud-born database, use basically all of the awesome infrastructure we have as part of Azure. We have 30 different regions. We have these massive data centers. How do we actually build a NoSQL database that takes advantage of all of this infrastructure? In 2012, we saw AWS also release a NoSQL database that's similar in this space called DynamoDB. And we previewed DocumentDB. And in 2014 and GA'd it in 2015. Some of the benefits that we got coming a little bit later into the market is we got the benefit of hindsight. We learned all of the pains of how do you develop applications in the face of, well, what do you do about transactions? What do you do about queryability? What do you do about consistency? And we use this to basically build a much, much better NoSQL database. And I'll kind of tell you a little bit about how we view the world. At a high level, you can think of storage mechanisms kind of in 3 different buckets. One is relational databases, NoSQL databases, and data lakes. If you ever go to Microsoft Azure's website and go to like data, it's very confusing to navigate, right? There's like a crap ton of things on there. So I'll kind of tell you about what these 3 categories are about. For relational databases, we wanted to build a world-class database for scaling up. These are heavily read optimized. We now have all these really cool like in-memory OLTP functionality, so you can get like millions of reads per second. But what if you want millions of writes per second? They give you very nice index and query processing on a single box. But the thing is that we have spent 20 years perfecting this space, and we also found that this brings a lot of legacy that we cannot get rid of, right? Like once you introduce relational joins, you can't really step away from that. And then when you go and say, hey, time to shard my database and scale beyond that, you're going, wow, this thing is painful. So for NoSQL, what we do is we build a world-class scale-out database. These are both write and read optimized, meaning we can ingest highly concurrent number of writes coming in. It's completely lock-free. This allows us to be able to do this. And we give you awesome query and indexing capabilities on top of that. We also have this category of things called data lakes. You can think of this as storing like almost like a blob store. You can store a bunch of unstructured data for doing massively parallel compute, things like Hadoop, or in this case, Azure Data Lake Analytics. On top of that data, this tends to be very write optimized, but on the read path, the latency tends to be high, right? You're doing very, very heavy reporting and analytics kind of workloads where it's OK if it takes a couple hours. If you actually let a user, let's say you back a website on this, if a website takes a couple hours to load, and your users won't be happy, I'll tell you that. So for the purposes of this talk, I think NoSQL fits in a very nice middle ground here. And we'll talk a little bit about that. One thing that I think is a bit of a misconception, this is just kind of how NoSQL has evolved. A lot of people tend to categorize NoSQL in terms of the data model. So you might be used to seeing people say, like, oh, that's a key value store, that's a document store, that's a wide column, that's a graph store. The thing is that almost every modern NoSQL database is moving into a multi-model world. So if every new NoSQL database supports every data model, then how do we actually differentiate these products? So let me kind of tell you about at least how I view the world. We came up with basically a set of problems that we wanted to solve. And you can think of this as the problem of, do you want to be happy or do you want to be rich? Well, ideally, I'd like to be both. Is that possible? So let's talk about some of the trade-offs you have to think about when you're building a database. Number 1, programmability versus availability. When I mean about programmability, this is the concept of if you ever build a distributed system, you're probably looking at Brewer's cap theorem right away. Or even better, Brewer's cap theorem basically tells you about, in a distributed system, you have these concepts, consistency, availability, and partition tolerance. Consistency is if I distribute this application across multiple nodes, what is the behavior of reads when I have writes? If I write to a set of replicas, do I block those replicas before serving reads? That means things are strongly consistent. But you know what? I'm sacrificing availability and latency here. Those replicas are not doing anything. They're just blocking. Or do those replicas just serve requests as fast as possible? I can get very, very low latency with very, very high throughput, but I'm getting stale reads. This is the concept of eventual consistency. Turns out eventual consistency is very, very hard to program against. And so how do you actually manage these trade-offs? Can I get something that has good availability and latency characteristics, but is also easy to develop against? Let's talk about scale versus distribution. For scale, you can think of this as every database likes to say it's elastically scalable. There are a few databases that actually do this very, very well. The ones that don't do it well give you some tools for rebalancing data and go, hey, you want to scale up, you want to scale down, we give you some tooling, good luck. And during your scale up process, you're going, man, I don't want to take my website down. How do I keep and maintain the availability of this website while I'm rebalancing all this data across a greater number of shards, right? Well, it turns out some databases give you ability to do this. You can scale up, down on demand without having to sacrifice availability. And the thing is, what makes this difficult is now if you want to replicate this into multiple regions around the world. So if I want to elastically scale up and down, and also just add and remove regions, how do I solve that problem? The problem of latency versus durability. Everyone likes to have low latency numbers, and it turns out there's a lot of databases that also cheat this. What they do is they buffer things in memory before they flush to disk. MongoDB is notorious for this. What they'll do is they'll say, hey, I've written a record, and they'll say, yes, I've totally written that record. What they're actually doing is holding it in memory, and then tomorrow, if you, let's say, have a hiccup, just a hardware blip, that node reboots, you go, hey, man, I thought you wrote that record. And the database is like, no, I lost that, sorry. Sorry about that. What we want is durable commits. We actually persist records to disk so that in the, in the face of failure, you still have high durability for your data. I mean, it's kind of like a cardinal sin for a data store to lose data. But how do you do that with low latency now? The other problems that I find that's very hard to balance this trade-off is transactions versus scale. It turns out that distributed transactions are just hard. It's a hard computer science problem. This is why even when you look at relational databases that give you awesome transactional semantics, you lose referential integrity in transactions once you shard a database. You don't get that kind of transaction scope beyond multiple shards. So how do we solve this problem of, well, do we just throw away transactions to be able to scale out? Well, it turns out it's pretty hard to develop an app if you don't have transactions. So how do we scope that transaction so that you can get transactional semantics across multiple records while still doing this at scale? Query and schema management. I talked a little bit about, data can evolve quite quickly. There are also certain type of applications where you're dealing with, fluctuating data that has is just heterogeneous in nature, has different properties. How do you provide rich queryability over that while still making this schema agnostic? Like one way of handling schema changes is I'll just throw it all in one big string, and the life is good, right? Well, the problem is that now when I want to pull that out and query it, like what good is a database if you can write records but not query it back out? So how do we provide rich queryability over this? And then lastly, I think there's always the trade-offs of cost versus performance isolation. You can think of this as if I deploy an application on-premise or even on a set of dedicated virtual machines, I get really, really nice performance isolation. I can make sure that no other tenant, let's say no other person's workload will ever bother my workload because these are my machines, these are my VMs. But the thing is that you're probably provisioning for peak, and most of the time these are underutilized. And so this tends to be a really, really expensive way to build things. On the other extreme, you have a bunch of multi-tenant cloud services who, because they can pack multiple tenants on a shared set of resources, they can offer a much, much lower price point, right? So they can offer much lower total cost of ownership, but then you end up with the classic noisy neighbor problems. One guy writes crappy code, uses up all the CPU on a box, and everyone else is going like, well, what's with this? Like, why does performance suddenly suck? And so how do you get airtight performance and low total cost of ownership? These are kind of the different trade-offs I view that are very difficult in databases. Oops. And I totally believe it's possible to both be rich and happy. And hopefully by the end of this talk, this is kind of the vision of what we want to build. and I'll kind of tell you a little bit about the capabilities on how we try to move and push the envelope in this direction. So let's talk about going back to the problems of volume, velocity, and variety. Let's talk about this in the context of one of our customers. So one of the guys that made a bet on DocumentDB early on was this game studio called Next Games. And what they were doing was they partnered with AMC to build a video game for the Walking Dead TV show. And what they found was this is actually a pretty hard problem to solve. Games are a little bit different from other applications in that most applications, like if I build DocumentDB, the number of users, the number of requests steadily goes up over time. Games actually work in reverse. What ends up happening is you do a bunch of PR, or let's say the Walking Dead season's about to come out, so you need to launch and capture as many users as possible. But then if you don't get to steadily plan out capacity, how do you actually handle this uncertainty? How do you handle and scale on day one? Because if you don't scale on day one, there's a lot of very high-profile games that totally screwed up their launch, and you don't get, this is an unforgiving space. If you screw up your launch, people just say, this game sucks, I'm never going to play it again. And games tend to not actually age very well. Not a lot of us like to play 10-year-old games or 5-year-old games. For a large chunk, this means that you need to be able to handle and scale for unpredictable traffic on day one, and then gradually scale this back to reduce the cost of running this system. On top of this, once you've captured all of these users and they go, hey, this game looks fun. Let's say the TV show, the season just came out. How do we actually make this a game that people want to keep playing over time, right? We want this to be engaging. I mean, one of the go-to things for making a game engaging is incite some competition, introduce some social gameplay features so that people can play against their friends. And that way, if my friend beats my score, there's no way in hell I'm going to let him do that. So I'm going to make sure that I beat him. Now, for a social game, this introduces a few new technology requirements, specifically around latency. It's very easy to develop on a local computer to get like a robust low latency experience. The moment you're talking about handling, shipping network packets across and between players, how do you make sure that this is very responsive? How do you get very low latency out of this? The results for this game were actually phenomenal. So when they launched their game, they've actually done this twice now. Each time when the Walking Dead season comes back on television, this app becomes #1 on both the iOS and Android app stores. The amount of requests that they bombard on their database is incredible. They perform roughly 1 billion queries per day. But I think what's impressive isn't the 1 billion queries per day, but the fact that 99% of those are served in under 10 millisecond latency. So how do you do this, right? And why for them, they made a bet on DocumentDB. Like, what do we actually do in this space? #1, for this category of apps, we are truly elastic. You drag a little slider and say, hey, I need to scale 100x more throughput. DocumentDB handles all of the partition management behind the scenes. You don't have to think about the world in terms of physical partitions. We will scale that app up, and we will maintain availability while the app is scaling up. And we also allow you to distribute this app or your data across multiple geographic regions, so you can dial this throughput and spread this across different regions. We've also seen people take advantage of this for a different category of applications. We have one customer who's an e-commerce retailer, and what they find is that their traffic is actually predictably bursty. Every Q4, around Black Friday, Cyber Monday, they had to scale up about 10x. And immediately after everyone's spent all their money and Christmas is over and everyone's broke again, well, it makes no sense to actually pay for all this infrastructure, so it's time to scale down. And so what we saw was this pattern for them where every November they'll start testing, and as the holiday season approaches, they just ramp up from 2 million to 12 million requests per second for provision throughput, handle all of this workload, and then dial this back down. And so being able to do this on demand and paying for this by hour So even if your application isn't, let's say, seasonal by day, but let's say it's seasonal by hours, where you have an application that, let's say, is hot from hours 9 to 5, tends to be a business group of users, you can dial up throughput during those hours and then dial this back down. You don't have to provision for peak. DocumentDB is also elastically scalable in terms of storage. So basically, the way we do partitioning is we look at, we have some smart logic that calculates what's the minimum number of partitions needed to serve the storage and how much we need to serve or give you in turn, how many partitions we need to serve the amount of throughput. If we take the max of these two values, we've basically made sure that there's no bottleneck in terms of storage or throughput. You can then think of the world in these two different dimensions, and we'll kind of just allow you to elastically scale on both of these dimensions. We also have a bunch of capabilities in the space for variety. So I mentioned latency. We basically build this database from the ground up, from scratch. This actually runs completely on bare metal. We built a rich resource governance layer. This is all C++, all the way deep down. But some of the things that we use to make sure that you always have very, very low latency. Number one is this is designed to be distributed from the very ground up. And so we have a very rich partitioning story for volume, as well as a very rich story around replication. We replicate all of this data 4 ways in a single data center, and then you can add additional data centers, each which will have a replica set. Now, having those additional replicas gives you a couple of things. Number one, it gives you a lot more throughput because you can distribute that workload across more machines. It also gives you some really nice availability characteristics because if one replica goes down, we'll automatically just tear it down and bootstrap another. Anyhow, for this, in terms of latency, we can actually bring that data and ship that data to where your users are. So if you have users, let's say, ranging from West US to here in Gold Coast, the last thing you want to do is ship a packet around the world. If you send a network packet across the Pacific Ocean, a round trip is about 300 milliseconds latency. If you want to now deliver single-digit millisecond latency, how do you do that? Well, you cheat. You go, speed of light, I don't know how to solve that problem, but I can cheat it. I can ship that data local to where the users are, replicate this, have rich semantics around consistency between this data, and then have people exploit data locality and query that data in a data center closest to them. So take that, speed of light. Now, the other things we do is this is completely designed on flash storage. This gives us just some nice low latency characteristics on the disk itself, as well as it's a completely latch-free database by design. So we give you this latency in the midst of very, very high throughput. The indexing capabilities also allow you to synchronously index all of these writes as they come in, meaning that they're immediately servable back out on the read path right away. The latency numbers that we typically see, we benchmark using a typical 1 kilobyte record. If you send, let's say, 1 million requests, 99% of them for reads will be delivered under 10 millisecond latency, writes under 15 millisecond latency. And for P50, the median numbers, they look even better. The reads are less than a single millisecond latency, and writes are under 6 millisecond latency. This is from the perspective of a request comes into the database and a request comes back out. Of course, you always have to account for network latency on top of that. So when you do performance benchmarking, it's best to perform these requests in an application in the same Azure region so that you're not shipping a packet around the world. Here is some benchmark numbers. We just did a load test on one of our clusters, 1 million reads per second and 1 million writes per second on a 1 terabyte collection. And these are the performance numbers that we saw on this benchmark. We saw reads under a single millisecond and writes under 15 millisecond latency consistently. I talked a little bit about distributing this data globally. Some of the things that we also add on top of this are a multi-homing API. So all of the endpoints are actually served under a single endpoint. This means that if one region goes down, you can actually gracefully fall back using a policy without having to redeploy the application. We also give you the ability to manually fail over, as well as for your own BCDR drills. But there's actually another interesting use case for this. Basically, the model is writes are finitized to a single region, reads are ubiquitous across all regions. If you find that tomorrow that all of your write pattern is not what you thought, you chose the wrong region and you want to affinitize to another region, a manual failover changes which is the primary region. And this is one way of rehoming where those writes go. We gave you some well-defined consistency models. I talked about the problems of strong versus eventual consistency. It kind of sucks when people have to, when they tell you like you have to go between these extremes. So what we wanted to do was we wanted to introduce a few additional click stops. In particular, we call this, these two concepts, bounded staleness and session consistency. So one of the big problems on eventual consistency is how eventual is eventual. If I just throw this data into the garbage, I can say like, hey, it's eventually consistent. Like, just keep waiting, man. Like, trust me, it'll eventually be there. A nice way to think about this problem is like, what if we can tighten up the bounds on how eventual can be? And so what you can do is for bounded staleness, you can actually define limits on both the dimension of time as well as the number of operations. If the secondary replicas start lagging behind in either of these dimensions, we'll automatically start applying back pressure on the write path to help allow the replicas to catch up. The other click stop in between, this is what we actually find most people use in practice, is session consistency. This is the concept of scoping a consistency to a single session. So like reading your own writes. A use case for this would be, let's say I have a social application. I'm posting on my friend's wall. I post some comments. And now, on the grand scheme of things, this web application needs to be very, very low latency. It needs to be highly available. So it's OK if I relax consistency and my buddy sees my comment, let's say, a second later. What's not OK is if I refresh the page and I go, where did my comment go? Did the application actually write the comment? Should I write it again? If I write it again and I refresh the page, am I going to see it twice? Like, what is the behavior? And this is what makes programmability for eventual consistency so hard, is you have to bake this logic into the application. With session consistency, we give you this functionality out of the box so that I'm able to read my own writes. I actually get strong consistency scoped to my session, while other sessions get eventual. So let's also talk about variety. This is the third V in our three Vs. And I like to think of this, the easiest way for me to rock this is by building a product catalog. And we'll kind of think about how do we build this in, let's say, the traditional relational model that we're all familiar with, and what this would look like in a schema-agnostic database. So in my product catalog, I sell everything, including coffee mugs. And for coffee mugs, I want to be able to, let's say I want to be able to query by the color of the item, whether it's microwave safe or how much capacity it can hold. Easy way to do this, I'll just create some columns for each of these different product attributes, and I'll index them so I can serve them back out on queries. Problem is I also sell a bunch of other things, like a service book. And I'm wondering, this is an interesting schema. Is this microwave safe? How much liquid does my Surface Book hold? It turns out if I actually ask the folks who build Surface Books, it's definitely not recommended for you to microwave this thing. It's not part of the specs. Instead, what I want to do with this is I want to create this product on a different set of dimensions. And you go, OK, well, this is pretty obvious, right? Like coffee mugs aren't laptops. You don't have to be a rocket scientist to figure that out. But how do we solve this? How do we actually represent this in a database? And this becomes a problem of if I just keep adding columns and indexing them, this becomes a very sparsely filled table very, very fast. This is not an efficient way to store data. There are some patterns for this, like if you abstract out a products table and a product attributes table and then join this, this will allow you to represent this data. However, the moment you need to do this at scale and shard across nodes, once again, this is kind of a broken story. This is where schema-agnostic databases are, I think, really beautiful. JSON especially, I think, is beautiful because it's self-describing. Every time you write a record, you're not just posting the values. You're also posting what these are. Like, is this storage? Is this memory? I can add and subtract records attributes to a record. And one way to think about this is I actually hate people who say schema-free, because schema never actually went away. If you don't know the schema, you don't know how to query your data back. But what this is doing is actually you're defining schema at a record level rather than at a table level. And that means every record can have a different schema. You can just add and remove attributes and then be able to index this on demand. So what do we do with this data? Like, why is DocumentDB interesting in this regard? One of the things that I think makes this interesting is we're not only able to ingest this data with different schemas, but we also are able to index it without knowing anything about it up front. This is because JSON can be very, very easily represented as a tree. If I were to think of that root node as a root of a document, each of the underlying properties are then the child nodes. JSON also has a couple interesting things. It's got some data types for objects and arrays. This allows you to denormalize and represent hierarchical relationships within a single record. If you do this in a record, basically from an indexing point of view, what we do is we just go deep inside the object and recurse all the way down to the lowest property until you have something that is a primitive, and then the leaf node is the value itself. Now from here, we just merge each of these records, or rather the index for these. And so because we're able to build an index using JSON as a tree and merge all of these trees together, we basically have built an inverted index. If you have played with products from the information retrieval world, this is actually not a very new concept. We kind of just took that playbook. But I think what's really cool is bringing this to databases. You can now automatically index every property of every record, as opposed to declare upfront, hey, look at this one column or look at this one path, and please index that. Instead, you can take a policy approach of, just index everything. And then I will tell you which parts of the tree later on when I want to tune this on what paths I want to leave out. And you can actually apply this recursively to an entire path with wildcards as opposed to property by property. So once you have ingested that data, once it's indexed, this is served back out. We made a pretty strong bet on SQL for the query language and JavaScript for store procedures, triggers, user-defined functions. Some people, I find JavaScript is a little bit controversial. I actually like it a lot myself because, JSON is JavaScript's object notation. JSON is inherently dynamically typed. And so having a language like JavaScript instead of T-SQL allows you to build very expressive business logic around this. It's a full-blown programming language, and it's a pretty natural way to interact with JSON. This only applies for the server-side programmability layer. We actually use, I think it's kind of cool, we host a bunch of Chakra runtimes, the same JavaScript virtual machine that gets shipped with the Microsoft Edge browser. By the way, I really wish the browser guys would do that VM more justice. It's a beautiful VM. And basically, we have a pool of these to allow you to do this programmability logic. This is the mechanism by which we also expose transactions. And so the way transactions work in DocumentDB's world is, in order to give you multi-record transactions while still kind of scoping this to avoid having to do a distributed transaction, is these are transactions are scoped to a store procedure, which is scoped to a partition. And basically, you can think of, when I write this business logic, let's say it does a sequence of reads and writes, it does some data validation. If I want to roll this back, I use the throw keyword to throw a exception. If I allow this to complete successfully, this is the equivalent to a commit. And so you can get these all or nothing semantics, full ACID semantics around the multiple records for a body of logic. Really, while the 3 Vs are interesting, I think actually the real kicker here is this is also done. It's managed as a service, and so it turns out not a lot of people really like setting up, let's say, 100 node, 200 node database deployments, spending a week to do that, and then let's say next week your boss comes and goes, hey, we want to add another region for disaster recovery. Do that again. And it's like, okay. And then once you add another region, maybe you want to add a couple more regions for low latency characteristics around different geographic regions. Because it's fully managed as a service, you actually, you literally click a little button. We will provision the entire cluster. We'll let you then, at a click of a button, add additional regions, remove regions. And then we give you SLAs on top of this, in particular 99.99% availability. And this is true. DocumentDB is actually always on. We don't have to come up with a new thing that's always on. Because it's distributed by nature, the architecture for this is actually we spin up these giant clusters. This is built as a multi-tenant service. And these clusters are spread across 10 to 20 different fault domains. Fault domains are just a way of saying they are spread across different physical racks, so that if, let's say, network connectivity got chopped by, on a certain rack, the cluster itself is resilient against that. And so because each of these nodes are spread across 10 to 20 fault domains in each of these Azure regions, this gives you a high amount of resiliency against hardware failures. They're also spread across multiple update domains, so that service updates, like when we update the database to introduce new capabilities or we need to patch something, this is all transparent to you, because now that the physical nodes are distributed this way, when we spread out partitions and we then replicate each of those partitions, those are spread across all of these different nodes who live on different fault domains and update domains. This is just some of the techniques we use to give you 99.99% availability. On top of this, we actually give you a bunch of, we're the first, I think, cloud service to offer SLAs around latency, consistency, and throughput. And so basically, from a latency perspective, those numbers I mentioned on P99, less than 10 milliseconds for reads, less than 15 milliseconds for writes, we actually we're drafting and working with our legal department to be the first guys to actually guarantee that. On top of this, we also guarantee consistency. So each of those different 4 consistency modes, we honor those. We fully back that. And if you ever get a stale read, we put money down on this, where if you can actually find a stale read when you shouldn't, then we've basically violated our SLA, and you get a refund. And then the other thing is throughput. So I mentioned this trade-off between designing a multi-tenant application and then solving the noisy neighbor problem. The way you solve this is you actually just write a resource governance layer. Basically what an operating system does, governs all the requests in terms of how much CPU, how much memory, how much I/O requests are actually budgeted. This is very, very tedious and very time-consuming, but we went ahead and did it. And so this actually allows us to basically offer this giant cluster, this NoSQL database, at a much lower price point than you can ever actually achieve by if you were to run this on, let's say, dedicated VMs. And you don't get noisy neighbor problems. So the model is, instead of having a fully consumption-backed model, what we do is we have a provision throughput model. And you can think of the throughput model as we give you request units. You can think of these as, like, I have a token bag system where every time you make a request, I take some tokens out. Every second, I put some tokens back in. If you use up all of the tokens, then we throttle. We basically tell you, hey, you either need more tokens, or maybe you have some requests that you want to optimize to use less tokens. But we were going to tell you to retry. Now, coming back to throughput and guaranteeing this, this means that if you, let's say, allocate and provision a database to handle, let's say, 1 million requests per second, it's not an upper limit. This is now guaranteed. At any given moment, if you need, let's say, 1 million requests per second, those system resources are budgeted and set aside for you. So this gives you very, very predictable performance and this throughput available to you on demand. Once again, if you find that you aren't able to saturate this throughput, we actually guarantee this with our own SLA as well. We're very proud of what we've built. To give you an idea, since our general availability launch, here's what daily availability has looked like. While we give you 4 nines, we actually believe that, and think about 4 nines, this is a single region. We believe if we do multi-region deployments, 5 nines is totally doable. So I talked a little bit about multi-tenancy and TCO. I just realized I put this slide in here. But we have a paper where we actually did performance testing on a Cassandra cluster on dedicated VMs. This is actually some follow-up TCO paper that AWS did when comparing cost of ownership of DynamoDB versus open source NoSQL on VMs. What we found is when we repeated that experiment, we not only verified that their findings are correct, but we actually found that for the workloads we tried, basically anytime you add indexes, DynamoDB actually puts a direct multiplier on the number of write capacity units, driving up the cost. So very quickly, you'll notice that if you add any indexes, the bill is very expensive. For a typical workload, DocumentDB is going to be 3x cheaper than DynamoDB. You can find this TCO right up if you want to reproduce this experiment on our website. So OK, those are like an interesting set of problems that NoSQL and DocumentDB can solve. I talked a little bit about product catalogs and gaming. But I mean, when is this actually a good fit? Where do we actually see people using this kind of technology? And this one, we actually, I mean, because we're a cloud service, we just looked at, who are our customers and what are they doing? You don't actually have to get inventive here. We can just look at, what are the patterns and trends that we observe. IoT, it turns out a lot of the problems are the exact same. When you have lots and lots of sensors, it turns out if each of these sensors are emitting a record at every second, you're dealing with very, very high volume. In fact, this is probably the highest volume I see in terms of workloads. And this is because if you think about applications, humans actually don't click and generate events every second. But a machine will. And so when you're dealing with lots of these sensors, how do you actually deal with this high rate of ingestion for events? How do you then be able to build rich applications that can do things like anomaly detection? Like, for example, if I have a bunch of smart meters for manufacturing, and I'm measuring the temperature, and if I know that the temperature goes up, my whole batch of what I'm producing out of this factory is ruined. So I need to be able to react very quickly to these anomalies. How do I deliver low latency queries over this data set to be able to give you this ability to react to it? And the other problem is each time I build a new generation of hardware, I might change and add a few sensors. And it turns out hardware is, relatively speaking, a lot harder to update than software. Software, I can just go and give you an update. For hardware, actually going to each of these physical devices and let's say adding a new set of sensors is quite expensive. And so what you end up happening is with each generation of hardware that you push out there, you end up with a different schema. And so one of the customers that is taking advantage of this today that we're working with, they're a top 5 automobile manufacturer in the world. Basically, every time that you drive around, if something happens, let's say like you get in a bad car wreck, the airbags are deployed, they will actually call you and give you some white glove service and say like, hey man, are you okay? And if you don't respond, they will actually call emergency services for you. And so they build a bunch of these services for their newer generation of cars. If you go and buy any of their new vehicles, their luxury vehicles, they actually give you these kind of nice services. Same thing with if an engine light turns on. Suddenly, like something's wrong with the car. They can actually detect that right away and tell you, hey man, maybe you should come in for service and we'll get this taken care of. And so they originally actually built this application on MongoDB, and the thing didn't work out very well. And so we worked with them, migrated it over to DocumentDB, and this actually allows them to perform basically high rate of ingestion of sensor data and do very, very fast queries on these events to deliver these driver safety and diagnostic services. Typical pattern on how would you actually implement this. I'm just using this as a example, but this is actually like a pretty common pattern and recurring thing. What you need is basically something like a message queue to help buffer spiky workloads. Normally, instead of just relying on batch processing, if you want to do something in real time, you'll have a stream processor. We have things like Spark and Storm on HDN site to do this. We also have a PaaS offering, Azure Stream Analytics. And this is where we were for these guys, they use DocumentDB as a hot store to actually do anomaly detection, as well as doing a second write to something like Blob Store as a cold store or Azure Data Lake, where you can basically get the best of both worlds in terms of DocDB gives you low latency and awesome queryability, which is what you want for recent data, for hot data. But this comes at a cost. You can then also save this to some colder storage to do long-term analytics on this data set. DocumentDB also has a relatively new feature we call change feeds. Anytime you perform a mutation, a create, an update, any kind of write, you can actually get a very efficient mechanism for pulling out any kind of changes out of this, and then build something like, let's say, a logic app or Azure Functions that reads this change feed processor. And then if they see an anomaly, let's say a spike in temperature, tell IoT Hub, hey, go perform an action and solve this, basically rectify this. You see a temperature spike, maybe try to bring temperature back down. We also see a lot of usage in retail. I mentioned a little bit about moving traffic up and down for seasonal demand, like Black Friday or Cyber Monday sales. But some of the other problems that you'll see, that's the problem of volume. A lot of these data stores have requirements around, if you have a global website, you have a global user base, you want to deliver low latency access to that same data set around the world. But even more so, there's some very, very latency critical workloads like personalization and recommendations. Basically, we see a lot of folks do things like, if you want to do a recommendation, let's say try to drive up the amount of conversions you get for advertisements or what products you recommend. If you are now blocking rendering a page to look up who this customer is, and then quickly go, hey, this is Andrew, and Andrew really likes video games, so how about we advertise a video game for him? You need this to be very low latency for me to actually have a good experience on the website itself, right? And so this is where low latency data stores are quite popular. And then I kind of showed you a product catalog on how both the data in this space can vary quite a bit in terms of schema. But this is true for just also doing things like events for personalization if you want to do, watching click behavior or just engagement metrics on each of these different events might have a different schema depending on the context of the application. Some of the things that we're seeing in this space, one is we're working with one of the top food retailers in the world. They basically have 2,000 stores that are distributed across both the EMEA and APAC regions. And what they wanted to do was guarantee high availability and low latency to this global user base. What they ended up doing was they used the global distribution capabilities to set up an active deployment across Australia, Japan, and Europe. That way, all of these users get very, very low latency. One of the other things that they found was a massive improvement was they used to run SQL on IaaS. They ran into some regional outages that really hit them bad. This was for an online ordering processing system. Anytime you order food on their online website, it gets processed through here. But by having this distributed across regions also helped them improve this reliability a lot faster, or a lot better. Basically, here's kind of an idea of how you would do this. You can deploy your application in different Azure regions, let's say Japan, Australia, and Europe. Put these behind an Azure Traffic Manager, which is smart enough to understand where a user is and route that traffic to the right data center. From here, you do a single DocumentDB that's globally distributed across these regions. And that way, each of these applications can then query something local to them to get very low latency. And in the event of, let's say, I don't know, tomorrow a meteor comes striking down Earth, we might be concerned about I guess the meteor, but your data is safe. What will happen is, even though this data center got kind of owned, those requests will get forwarded automatically to another region. So at least you don't have to worry about your data. We'll probably worry about all the other problems from that. Another space that we're seeing a lot of usage for NoSQL technologies is in the space of ad tech and social analytics. We see a lot of or in this space, for a lot of the customers working in this space, number one of the problems is you have lots of user profiles. For these guys, specifically Affinio, they're a startup working on basically understanding all of the users for, let's say, the industry that you're working on and giving you some social analytics on how do you actually do better targeted marketing for this. They track over 1 billion Twitter profiles around the world to try to get an idea of what causes people to get engaged. And when you're dealing with this number of profiles, you're dealing with a very, very high rate of ingestion and storage. You'll notice right away, like for each of these different problem domains, it ends up being the same problems. It's volume, velocity, and variety. Once again, you have a global user base. You might be using this to drive some real-time bidding for advertising. So if you have, let's say, kind of like a Dutch auction system where people can bid what a cost per click is before rendering the actual advertisement, you have something that's very, very latency sensitive. Or if you're doing any kind of personalization, once again, if you're blocking rendering a web request, you need something very, very low latency. And when you're also dealing with, let's say, something like integration with Twitter and pulling user profiles from this or any kind of third-party data source, at the end of the day, like, who gets to dictate the schema now? You've just handed the keys for a schema to them. If their JSON API changes tomorrow on what the response looks like, you don't want your application to break. At the very least, you want to make sure that the data store is still capable of ingesting this data. You might have to tweak some queries, but you will never have any data loss because you're not doing any kind of pulling values out of a schema just to be able to fit it into your data store. We're working with one of the top 5 banking and financial services firms in the world on basically an application to do recommendations. They also do things like credit cards. So if a user has, let's say, poor credit, they might advertise something like a low interest, low APR card. If they see someone with very high credit, rather than advertising that, they're going to advertise, rewards cards, something that gives you lots and lots of cash backs or lots of points. They capture a lot of this real-time also behavior from the user, so they know that if they're shopping for credit cards, they should recommend a credit card. If they're shopping for mortgages, maybe recommend that instead. They use Spark to basically build a model for this, and then they store all of the user profiles in DocumentDB, mostly for these low latency characteristics, but also for the ability to scale out and handle lots and lots of events in real time. One of the architectures that I've seen used out there that these guys are also kind of doing for their personalization, they basically have a multi-channel marketing data platform that pulls user profiles from a number of different sources. They're using Spark on HTInsight to process this data set and put it into DocumentDB. In the meantime, when a user goes to a website, it'll go to, for the recommendation, an API app that quickly calls DocDB to understand who this user is and what their last few actions are. They already have a pre-populated machine learning model then to say, hey, if you see this kind of user and these kind of actions, give this kind of live recommendations. So rather than doing like a pre-compute recommendation, you can actually do, based off of recent user behavior, do kind of more real-time recommendations. They also have a separate pipeline for doing event hubs to stream analytics and storing a lot of these events into ADLS. And this is more of an archive for all of the events so that they can, over time, use this to run this back to their Azure machine learning model and improve the model for better conversion rates. Lastly, the other area that we've seen a lot of usage for NoSQL, gaming. I already talked a little bit about this. We actually use this in each of these areas. It turns out Microsoft is not a small company. We use DocumentDB very heavily in-house, like all of the social features on if you play Halo or use Xbox Live. Much of that is backed on DocDB. A lot of it comes down for gaming is the ability to scale up and handle bursty workloads, deliver low latency for a global user base, and as well as in this space, people need to iterate quite quickly. Productivity is quite important. So rather than having to define a model in the application, define a model in the database, and then tomorrow, each time you add a feature, having to go back and make sure that these two things actually talk to each other, having a database that's agnostic and be able to drive much of that model from the application allows you to just move a lot quicker if you're a big CI, CD kind of geek. Talked a little bit on Walking Dead already, so I'll skip this. But I mean, common architecture in this space that we've seen is for doing social gaming backends. A lot of the assets will be stored in Blob Store, which has great integration with CDN for doing media and those kind of assets. Then for actual user profiles, doing guilds, messages, leaderboards, backing that in a globally distributed DocumentDB. When you see certain things, like let's say a user has, someone beat my high score and I want to now react on that. For DocDB, what they'll do is they'll use Azure Functions, use that change feed, and use that to generate push notifications and tell, hey man, your score just got beat. You might want to make sure this doesn't happen. We've also seen people use HDInsight on top of this data set to do things like fraud and cheat detection, depending on the nature of what the game looks like. If you have something, let's say, especially like, let's say a casino type game where money is involved, doing fraud detection is very critical, and having a scale-out compute layer to watch game state is very helpful. I've done a lot of talking. I want to make sure I'm here to also answer questions. So I mean, and what I'm going to do is I'm going to basically break this out. Hopefully, in this session, you have a pretty good idea of at least why I think this is really cool, where NoSQL is kind of headed, and kind of the different scenarios where NoSQL databases are a great fit. If you are interested in actually building something on this, I'll tell you everything you need to know to be successful, best practices, as well as kind of what's headed on our roadmap in my session tomorrow. So please come check that out. I have a bunch of slides they told me I have to have. I don't know what this is. This sounds really cool, though. But anyhow, if you like this session, please commit or do the feedback. It does help us improve events like these. Otherwise, I'm going to open this up for Q&A.
Is there any on-premise version of it?
Is there any on-premise version of this? So I'll kind of tell you kind of the work we've done so far and where we're headed. Today, there isn't a on-premise story for production workloads. There is an on-premise story for dev test. So we have a high-fidelity local emulator that we just released a couple months ago. It actually it's got complete functional parity with DocumentDB. So from dev test, it's very nice. The future for production workloads is this is a core service as part of Azure, and kind of our roadmap for Azure Stack is all of the PaaS services, all the core ones we're going to make sure is available through that. And so it's kind of a matter of when, not if, we'll have something available through Azure Stack. But I don't know timelines for that just yet.
Yeah, we've got a project which we just put Cassandra in, and it's a security product.
Okay.
And it's all on-premise. It's all on-premise and
Yeah.
So it can't be cloud-based at all. But
Gotcha. Yeah, we realized there are needs for on-prem. I don't anticipate Azure Stack will land in the next couple of months, but this is something that we have planned.
nice, thank you very much.
Yes, question?
Is DocumentDB available now, or is it in preview? Is it only?
Is DocumentDB available now? Is it in preview? Yes, it GA'd in 2015. And I'll also tell you a little bit about our roadmap in my session tomorrow. But yeah, it's GA today.
Okay. All right.
It's already available in I think 30 different Azure regions. So
Okay, so
you're
most
also
of them-
you have good regional coverage. Yes, question.
If you actually want to keep your data in a single country because it's government data, something you can't leave, is that still possible? Can you limit?
Yes. So if you want to keep data in a single region, yeah. Even if you wanted to replicate to additional regions, we don't pair regions for you. Instead, you manually configure which regions. So even if they're let's say a set of data centers that are okay for let's say a certain government body, you can manually configure those.
So is the focus of this it's handling transactions versus say something like SQL Data Warehouse where it's more of an expert?
So how does this compare to SQL Data Warehouse? I actually see SQL Data Warehouse and DocumentDB used alongside, basically how you mentioned. DocumentDB gives you very, very low latency and highly concurrent characteristics. It's very good for backing, let's say, running the actual website. SQL Data Warehouse, while it doesn't have great latency characteristics, it has very, very strong compute characteristics, right? It can do massively parallel computes for very, very fancy looking queries. And so what we see is people will back their website on DocumentDB, have an ETL job, and have that go into SQL Data Warehouse, and then run their reporting and analytics on SQL DW.
Can you talk about the cost of running DocumentDB against a straight SQL DB on Azure, just for the sort of like for like?
Sure. So cost of DocumentDB and how does it compare? Billing is actually based off of two factors. One is storage, and the other is on throughput. Storage, I think the public pricing, if you don't have like, I don't know, enterprise agreements or anything, is 25 cents per gigabyte per month. And then for throughput, it's a provision throughput model. This is how we guarantee that these resources are always available and you can get predictable performance. For each 100 request units per second that you provision, that's $6 a month. And basically, we went through many iterations. We first did like this S1, S2, S3 thing. Then we found that a lot of people wanted something in between. So this is why we split these two dimensions up and let you kind of raise and lower throughput on a very fine granularity, as well as doing a consumption model for storage. How this compares, I'll kind of be honest, the clusters that we run on actually mimic and are very similar to what the P-tier Azure SQL databases run on. And as a result, a lot of the pricing is very similar in terms of what you get out of an Azure P-tier Azure SQL. The other thing, I guess, from there is basically, what are you looking at? If you want something that fits on one node, Azure SQL is very, very good. If you have something that you need to scale out, then DocumentDB is very good. But the hardware is underneath is the same, so the pricing is very similar.
You were talking about data warehousing. Are there some possibilities where we could do aggregations on those documents?
Gotcha. So the question was, in case the rest of you didn't hear, was what's the story around aggregations and what can you do in this space? So aggregations is actually something that is on our roadmap. It's actually landing in the matter of a couple of weeks. The aggregates that we will support out of box are going to be basic things like sum, min, max, average, count with basic where clauses. So think select count where let's say record is active, but no group by. This is actually meant to be kind of a building block for heavier compute. So if you do want to do heavier analytics, you can either use something to ETL to SQL DW, or you can use this as a building block. We're actually building a Spark connector. And so what's kind of cool about this is the Spark connector is smart enough to do push-down predicates. When you do something like Spark SQL and it looks at that where clause, it'll actually push those down directly onto the Spark worker nodes and then talk directly to the DocumentDB replicas behind the scenes and push those predicates down using DocumentDB's automatic indexing to basically narrow the data set Spark needs to munch through, speeding up your Spark job on the compute layer. That's kind of what we're working on in terms of aggregates. And then it becomes kind of up to you on what particular scenario you have on what's a better fit. Do you actually do Spark jobs on DocDB directly, or do you use something like SQL DW for a data warehouse?
Going from DocumentDB to, for example, SQL data warehouse, you start losing the variety component to it.
Mm-hmm.
And that's the thing that DocumentDB becomes very good if you could do aggregation on its own.
Yeah. Basically, DocumentDB optimizes for low latency and high throughput, and so it tries to be very frugal on the amount of system resources it uses. And so the aggregations that you'll get out of box tend to be things that don't take a lot of compute resources, that basically don't need to preserve state for a long period of time. And so this is really nice for if you want to just do something like count the number of orders I have, or the number of active orders, or how many pages I have if you want to do, like, let's say, pagination. in terms of doing like heavy reporting analytical workloads, you'll want to use something like either DW or Spark.
This is a real one-on-one question, but joins across tables and DocumentDB. So you've got a rich structure in your table with attributes as you want to, but is it easy enough to join across entities?
Gotcha. DocumentDB does not support joins across documents nor tables. In our world, it would be collections. And so this is where data modeling you'll want to kind of revisit. Rather than building your data model based off of, let's say, the entities and using something like third normal form, instead you're going to actually fit your data model to the actual workload. I will note that you can represent certain relationships, like hierarchical relationships, by denormalizing within a document. But that doesn't mean you always want to denormalize. This actually comes with some trade-offs. The other thing that is kind of interesting in this space is collections don't enforce schema. As a result, you can actually mix different entities within the same collection. Because queries are scoped to a collection and operate very fast and efficiently in the absence of joins on these, if you do things like annotating documents with a shared, like let's say a relationship ID, you can actually pull multiple types of documents back in a single network request just by filtering on that on the where clause. If you then go a step further and annotate documents with like a type property, you can then narrow down exactly which types you want to have pulled back in this network request. But I'll kind of talk about this a little bit more in depth in tomorrow's session on, I'll talk a little bit on how you partition this data, what you need to think about, and how do you model this. Yeah. Any other questions? Yeah, thanks. Thanks, guys.